Okay, guys, chapter 23, part 3. Jump right on in. I'm going to talk about some more of the accessory organs of the digestive system, the pancreas. The pancreas is behind the peritoneum, snuggled in between that C shape of the duodenum. We talked about the endocrine portion of the pancreas at the very first part of the semester. Covered it very well, so I'm not going to go over it again. If you have any questions about it, you can contact me through our class meetings or email or however. Okay, as far as the exocrine portion, this complex acinar gland produces something called zymogen. Zymogen granules are simply little packets containing the enzymes needed to chemically digest food, and they're secreted in an inactive form. That's a big deal. All of these are going to dump into these ducts, exocrine, and eventually they're going to dump into this main pancreatic duct right there. We'll talk more about that structure in just a minute. The pancreas itself is going to produce about 1 liter, 1,000 milliliters per day of pancreatic juice, which has a large component of bicarb, HCO3. This guy is going to neutralize the acid that leaves the stomach in the chyme that is pushed into the duodenum. We've already said these guys are secreted in an inactive form. Now, talking strictly about the peptidases, those that are intended to break down proteins, we find that we have 3 peptidases: trypsinogen, chymotrypsinogen, and procarboxypeptidase. These guys are going to be secreted from the pancreas in an inactive form. Now, the brush border is going to have an enzyme called enteropeptidase. Enteropeptidase is going to take trypsinogen, activate it, turning it into trypsin. Trypsin itself is also capable of changing additional trypsinogen into trypsin. Trypsin will change chymotrypsinogen into chymotrypsin. Will also change procarboxypeptidase into carboxypeptidase. The reason these guys are secreted in an inactive form is these things break down proteins, and that's basically what our body is composed of. So if these guys get activated, they can actually start breaking down our body, digesting it. And if you recall, I told you that if you get a gallstone right here, that the flow of pancreatic enzymes will back up, and some of these guys will spontaneously revert to active form, giving acute pancreatitis. Okay, talking about some more, the sodium bicarb doing the neutralization, zymogens, the inactive form. We've talked about these guys, their function: digest protein. This guy is going to digest protein, but it's specifically going to take the end amino acid off the chain, off the end which has the COOH on it. Sorry guys, I can't draw that little with a mouse. And it's going to break this bond right here. So that's carboxypeptidase's function. The other enzymes release pancreatic amylase. We talked about salivary amylase that begins the breakdown of carbs in the mouth all the way down until they get to the stomach, where it ceases. The carbs are after they leave the stomach and go into the duodenum, whichever way you want to say that. Pancreatic amylase will help to continue breaking down. We also have something called pancreatic lipase that helps to break down fats, ribonuclease for RNA, and deoxyribonuclease for DNA. We're going to talk about these guys in more detail coming right up. Now, as far as cholecystokinin, CCK, and secretin, so the chyme that enters into the duodenum, we're going to have those enteroendocrine cells, which are kind of epithelial cells that make these hormones. But the presence of chyme is going to trigger their release. CCK and secretin, we've talked about their effect on the stomach. We'll talk about their effects on the pancreas and then on the liver and gallbladder. So these guys are released. These are endocrines, so they're going to go into the blood vessels. They're going to get out of the blood vessels into different places. Their effect in the pancreas. CCK is going to cause the release, the secretion of the zymogen, and secretin is going to cause the release of the bicarb. Okay. Bile salts and somewhat secretin is going to stimulate the liver to produce more bile, or to produce the bile that it produces more rapidly. CCK is going to cause the gallbladder to contract and push out stored bile, of course, eventually bring it down here where it will reach the duodenum. It will also, in addition to contracting this, it's going to cause the sphincters, which control the flow, to open up so that the bile can get through. Now, during the cephalic and gastric phases, we are going to have the vagal nerve is capable of causing minor weak contractions of the gallbladder. Okay, guys, this is going to be a little bit of anatomy. You're going to do this in the lab, but I'll go ahead with this. So the right lobe of the liver, left lobe, with the right and left hepatic duct. These guys merge together, and it makes sense that you would fit when two hepatic ducts. Oh, I'm sorry, yeah, right there. When these two guys merge together, they're going to form something called the common hepatic duct. Now here is the gallbladder, and the gallbladder is going to connect to the common hepatic duct, and this guy is going to be known as the cystic duct. So there's the right and the left hepatic ducts. They come together and they form the common hepatic duct. Cystic duct comes in here, and then what's down there is the common bile duct. They don't actually call that on this, but in any case. So it's going to go down there, and of course there's a sphincter there to control the release of the bile through here. There's a sphincter on this pancreatic duct, and then there's a large sphincter, hepatopancreatic, ampulla and sphincter, and then there's the papilla, which is the doorway through which the bile and the pancreatic fluids get into the duodenum. Okay, guys, gallbladder itself, pear-shaped, 3 to 4 inches, 30 to 50 milliliters of bile. This guy's got a serous component, and then a muscular layer, and then a mucosa that lay on the inside. The lining of the mucosa has rugae, just like we saw in the stomach, because this thing is capable of expansion to hold it. This guy stores bile. It concentrates it 5 to 10 times, and then it's going to contract and push the bile through the cystic duct and into the common bile duct, and then down through the ampulla and the papilla. We already said that CCK is going to be responsible for that. So bile is made in the liver, and it's actually stored here for that period, and then it's released whenever we eat that type of meal. Okay, talk about this. Now let me tell you a little bit about the way the PowerPoint is set up. It is set up extraordinarily good, I think. It's my opinion. And if they tell you the same thing in 3 or 4 different ways, which for physiology, that's great. Okay, so let's talk. We talked about amylase. We talked about salivary amylase. We talked about pancreatic amylase. So here comes our chain of sugars. Pancreatic amylase is going to break it up into something, these polysaccharides, into things called oligosaccharides, which are going to be about somewhere between 2 to 8 glucose chained together. Okay, now again, we've got some enzymes on the brush border. We got dextranase. Dextranase is going to take the oligosaccharides and it's going to break them up into disaccharides. Those disaccharides are going to be basically one of these. We got sucrase, maltase, and lactase. Those are the enzymes. This breaks down sucrose, this breaks down maltose, and this breaks down lactose. And as a side note, anyone who is lactose intolerant does not have that enzyme. So they can't break down the sugar and it just continues. But these enzymes are going to take those disaccharides and break them up into monosaccharides. That's how we absorb them, guys, is monosaccharides. Here you can see the polysaccharides, salivary pancreatic amylase. We get our oligosaccharides, and those brush border enzymes break it up into disaccharides or the dextranose, and then the other brush border enzymes, sucrase, lactase, maltase, breaking up into monosaccharides, which is how we have to absorb them. Okay, so going again, there is maltose, which is 2 glucose molecules together. If you've ever had a malted milkshake, you had maltose. This enzyme is maltase. Maltase going to break it into 2 glucoses. Now, the actual absorption is going to depend. Fructose goes through these cells lining the epithelial cells lining the small bowel through facilitated diffusion. It can do that because it's not going up, trying to go up a concentration gradient like this. Glucose and galactose are going up a concentration gradient. The glucose is much higher in here than it is out here, so in order to get this in, we're going to have to use secondary active transport. If you guys don't remember this from A&P1, pull out your notes or whatever, or you can talk to me about it, but probably just as fast to get your notes. Okay, so anytime we're pushing something up a concentration gradient, we're going to have to use active transport. Secondary active transport, we pump the sodium out using ATP. Now we let the sodium come back in, provided it brings glucose, or in this case, galactose. That's going to be called a symporter because both of these guys are going the same direction. Once it gets in, then it's going to go out through facilitated diffusion out the other end because it'll be higher here than it is here. Again, that's A&P1 topic, guys, but if you have any real difficulty with it, just let me know during a meeting or just shoot me an email. Okay, here we're talking about the same thing. Here's our epithelial cells, the tight junctions. There is some leakage of glucose and water. There's our fructose coming in straight in, facilitated diffusion. There's our glucose and sodium coming through the symporter, same thing. And there, these guys are all going out the other side to the blood vessels through the facilitated diffusion. And there's the sodium potassium pump that's setting all this up. Here, we see the same thing. We see the glucose and sodium coming in. We see the ATP used to pump the sodium out, which is keeping the sodium gradient low inside, which makes sodium want to come in. Here we see sodium itself being absorbed, and here we see amino acids. We'll talk a little bit more about those in just a minute, but they also come in through a symporter. Okay. Again, another overview, the starch and the that should be polysaccharides. Polysaccharides, the salivary amylase, pancreatic amylase, breaking it into oligosaccharides. The dextranase is going to break it into disaccharides, and then these guys are going to break it up Lactose and glucose together make lactose. Oh, excuse me. Galactose and glucose make lactose. That's milk sugar. 2-glucose make maltose. Sucrose is glucose and fructose. And by the way, sucrose, that's just the table sugar we use. Okay, that's the stuff you put on your cornflakes. The board they're talking about the glucoamylase is one we haven't mentioned before. Coming over here, this is a separate thing. The mouth is telling what's going on. I'm not going to continue to read the same thing over and over. I'll let you guys, you can do that, and then you can let me know what you don't understand. Okay, so here I told you we get with the proteins. So the proteins come in these very long strings. Nothing's really going on in the mouth. When we get to the stomach, then we get the pepsin. We talked about that. And also the high pH. We're going to break these long chains into smaller segments. Those smaller segments are called polypeptides. Now, when we get in here, the trypsin and the chymotrypsin, remember, are going to break these guys up into very small chains. Carboxypeptidase is going to start cutting it off one, say right there. And then it'll cut the next one off and the next one. We also have some brush border enzymes that are going to help us to break these guys up even further. Carboxypeptidase, that is a brush border enzyme, not from the pancreas, but a different one. Aminopeptidase on the brush border is also going to remove one amino acid only. It's going, instead of removing it on this side, it's going to remove it from this side, the side with the amino group. Dipeptidase is going to split the dipeptides into single peptides. Now, we can absorb these guys 1, 2, or up to 3 amino acids at a time. We're going to do it with a symporter with glucose, but unlike the sugars, we can absorb more than one at a time. So here's another thing: the protein proteases and the gastric pancreatic juice is going to break it. We get our peptides. Proteosis is just a type of polypeptide. Don't worry about it. The technical definition is not of any practical use for us in what we're doing. So eventually we're going to get these broken up into amino acids. And again, here we see tri-dipeptides or amino acids, co-transport, symporter, get inside there, and they are going to be, instead of going facilitated diffusion, they will be actively transported out. Now, these guys are charged, so they don't need any kind of carrier. They dissolve in water, but just fine. Another picture of it, the fragments, the pancreatic, the brush border enzymes. We see it coming in. We see it being pushed out on an amino acid carrier, and it's active transport, so it takes ATP. Okay. I think I really don't see anything new on here, but I really do like the way that they've got several different slides telling you the same thing. Okay, here's our overview. Pepsin, HCl, we're breaking into large polypeptides, pancreatic enzymes, small, and then the brush border, and are going to help us to break it into some di and tripeptides, some just a single. And over here, it's going to give you what's happening in each of the locations. Again, I don't really think it's useful to go over those individually. Okay, guys. Now let's talk about breaking fats down into smaller particles. Now this has its own special name, emulsification, big long name. It just means to mechanically break a big glob of fat into a lot of smaller droplets. Now we know oil and water don't mix. We know because these guys have got a bunch of positive and negative partial charges, and these guys are totally neutral. So they really don't have anything that they like. So the we turn these guys, we use our bile salts. They help to break these up into smaller globules. After these are broken up by this, um, the lecithin and from the bile salts, we're going to get these into smaller droplets. And then we're going to form these guys into something called a micelle. A micelle is basically like a plasma membrane. We get this phospholipid with the charged head and the neutral legs. So the neutral legs, which have no charge, face toward the oil droplet, while the polar head faces toward the water, which is what it's surrounded by. Less than mixes with oil and water, micelles, don't really see anything there. Here we're going to talk about it again. So we get this large fat droplet, the bile salt, which is mechanical digestion, small fat droplets. We're going to have these guys surrounded. Now, this is where the pancreatic lipase comes in. These guys are going to be triglycerides, 3 fatty acids with a glycerol. And what we're going to do is we're going to cut these guys and break them apart into monoglycerides and fatty acids. So we get that monoglyceride and our fatty acids. There we go. Here's another way of looking at it. There's a monoglyceride right there, the free fatty acids, and the bile salts are surrounding them. They're breaking them up, and these guys are being surrounded by the lecithin, the phospholipid. These guys are going to go to the border. This is the microvilli on the epithelial cells lining. These guys, since they're lipids, they're going to go straight through. They have no need of any transport. Now, once they're in here, they're going to be packaged because since they are neutral, they're going to have something that is going to be polarized on the outside and neutral on the inside. And this thing is going to be called a chylomicron. This chylomicron is going to, if you guys remember when we were talking about the lymphatics, I told you these guys are going to be absorbed into the lymph vessel, a lacteal, where they'll go all the way up and eventually be dumped into the venous system. Another picture of several fat globule, the bile salts, droplets, the micelles, and inside here is where the pancreatic lipase is going to break these triglycerides up. These fatty acids, monoglycerides, some of the bile salts, these are going to be absorbed. We already said that they're basically going to uncoat right there and eventually get there. Let me look here, guys. I don't think there's anything here. Nah, there's nothing there that I haven't already talked about. Fat globule, lecithin, the micelles, showing the pancreatic enzyme, breaking it up. We also get fat-soluble vitamins and cholesterol in those micelles. So there they go, and there. The Golgi is going to. Okay, I'm sorry, guys. I'm having a hard time seeing it so small, and I can't make it any larger. So there's the protein shell, which is going to be our chylomicron. The Golgi is going to process this chylomicron in a secretory vesicle. We're going to put these guys in there. We're actually going, I guess I should mention, we're going to take those monoglycerides and fatty acids and we're going to put them back together as a triglyceride. So triglycerides, phospholipids, the fat-soluble vitamins, cholesterol, all of these guys are going to be put in the chylomicrons, and then they're going to be through exocytosis, they're going to get to the lacteals. 95% absorbed. We use the bile salts. This is just another picture of it. There they come in, the Golgi, the chylomicron, all the same, guys. As far as our little overview here, these are really good. I really like this. Lingual lipase, which we know doesn't activate until it gets to the stomach. Gastric lipase, emulsification, which is the bile salts breaking it up. Pancreatic lipases, breaking the triglycerides apart. And then here's all the things and where they happen at. Nucleic acids, pancreatic ribonuclease or deoxyribonuclease, brush border enzymes, nucleosidases, and phosphatases. These are going to break up the 5-sided sugars, which is ribose and deoxyribose, the nitrogenous bases, and then the phosphate ions. Small bowel is basically where all this is going to happen. Okay, here they've got a chart that's showing us, let me do that again, guys. See if I can draw it a little bit straighter. Here's the one that's showing us all the different secretions, the things that are secreted and the things that are absorbed. So from the pancreas comes, this is our main tube right here, okay? So lipase and pepsinogen, pepsin right there, HCl. We've already got our salivary amylase and lipase here. There's the bicarb from the pancreas, the pancreatic enzymes, and of course the bile salts. Jejunum, all of the brush border enzymes. Now we're going to reabsorb some of those bile salts, most of them, and these guys are going to actually be sent back to the liver and be recycled, breaking up the oligo and disaccharides into monosaccharides, the absorption, and here we leave the bowel, small bowel, and enter the colon. At this point, the colon is going to absorb basically salt and water to try to maintain it. If you were to add these up, 2,000, 1,500, 2,000, 500, 15, and 15, there's 9,000 milliliters or 9 liters of fluid that we put in there. So it's 1,500 from our saliva, 2,000 from the gastric secretions, 500 from bile, 1,500 from the pancreas, 1,500 from the intestine. This is how much in the small bowel we're going to get 8,500 out of that 9,000 back. In the colon, we're going to get another 400. So we're going to eventually get 8,900. 100 is going to leave in the feces. So this is how we keep from dehydrating ourselves during this process, because we use a lot of water in this process. Okay, just an overview, mouth, what happens. We have pretty much talked about this, so I'm going to let you guys look at that chart. I don't think there's anything new there that I can add. But if you have questions, let me know. Now, this is something that's kind of important in geriatrics. As people get older, everything in their body works less well. It's just wear and tear, guys. GI, the amount of secretions decreases. The amount of absorption is less efficient, which is why you get more gassy because the more that you pass on to your colon for those bacteria to use, the more gas you're going to produce. Peristalsis itself slows down, and people have a tendency for constipation, but I mean, there's all kinds of bulking laxatives to help with that. Because the absorption, people can actually be undernourished. We've already saw the diverticulosis, and that's part of that is going to be from the lack of bulk. Fecal incontinence possible, and colon cancer is the third killer, males and females. All right, guys, that's done with the digestive system, and we'll jump on the next one. Thanks.